So we can visualize complex functions, functions whose input is a complex number and whose output is a complex number. The best way to visualize them is as transformations of the complex plane, where we can sort of take both the input point and the corresponding output point, plot them on the same copy of the complex plane, and thereby look for relationships. So what is the transformational properties of that complex function? In this video, I want to look at a few examples of the kinds of insights we can gain from doing this by sort of taking a flyover of several different types of complex functions and maybe looking for some of their transformational properties. This is going to be a lot of what you do in this week's investigations, is relating these geometrical transformational properties of these functions to the algebraic properties of those complex functions. And so the analogy, the place where we've done something like this before as math students, is in linear algebra. So in linear algebra, we think of linear transformations as transformations of real vector spaces. So for example, when the real vector space is the xy plane, I can define a linear transformation by 2x plus y comma x plus 2y. In other words, I can supply a square matrix, a 2 by 2 square matrix, in this case 2, 1, 1, 2. And I can visualize its geometry. I can get geometrical transformational insights about it just by placing the domain plane on the left and the image plane on the right, and then by sort of messing around with stuff in the image plane, right, and seeing what happens in the codomain. So I've chosen this particular matrix, 2, 1, 1, 2, because it goes by the name of the cat map in linear algebra and dynamical systems, and so that's what inspires the use of this cat graphic to investigate what's going on here. And so if I change my inputs, I can sort of observe how the corresponding outputs change. After all, a function is a relationship between input and output. The function is not the inputs, the function is not the outputs, the function is the relationship between the two of them. So as I vary this vector, which is my input vector, I can observe how the output vector varies. And if I can do that with vectors, I can also do that with entire subsets of the input plane. So that's where my cat comes in here, right? And I can move this subset around a little bit and kind of see what happens. And if I play around with the function a little bit, I can change the definition. In linear algebra, this is a large part of what we do when we study the geometry of linear transformations. I can change some of my coefficients, like if I change the x coefficient in the first variable to -1 instead of 2, right? Now I get a very different looking transformation. My original transformation, the original cat map, looks like it has the effect of kind of stretching this cat away from the origin and kind of narrowing it, skewing it in a certain way, right? But if I flip this to a -1 instead, it looks like now we're stretching in a different fashion, but then there's also a little bit of a reflection happening, that the little spot on this cat's chin is on the opposite side, over here in the image plane when I've changed the function a little bit. And so we can get geometrical insights from the algebra, and we can get algebraic insights from the geometry. And all we have to do is look at it as a transformation, where I have the image on one copy of the coordinate plane, and I have the pre-image, the domain, on another copy of the coordinate plane. We could, if we wanted to, put both of these planes and overlap them. Right? I just wanted to start with this example with the two of them separate to help us understand. This is what we tend to study a lot in linear algebra. Now, in linear algebra, linear transformations can only do one of 5 things, transformationally speaking. They can dilate, in other words, they can either stretch away from the origin or shrink towards the origin in a proportional fashion. They can reflect across whatever hyperplane through the origin that you like. They can achieve a rotation around some axis that goes through the origin. They can achieve a projection, which is to completely squash away one or more dimensions in an orthogonal fashion. And they can skew. They can like take a stack of papers and kind of push it sideways, turn a square into a parallelogram without varying its area. So it's kind of only 5 things that a linear transformation can do in linear algebra, geometrically speaking. One of the questions I'm going to have us think about this week is, what about complex functions? What can complex functions as transformations do that linear transformations cannot, and vice versa? So that's going to be one question that I want you to spend some time kind of teasing apart as we go through the investigations this week. Now, coming back to complex functions, away from linear transformations, let's take some basic examples. Starting with, what does it look like if I have a transformation which is defined just by adding a complex number? So the function f of z equals z plus a constant. I'm adapting this from one of Steve Phelps' activities on Geogebra. He wrote this one for multiplication that we're going to look at next, but I adapted it to be addition. And so depending on the value of the constant a, if a is equal to 0, f of z is equal to z, this is just the identity transformation that doesn't do anything to any point. It just leaves it where it is. But if I take my a value to be 1 or something like that, now I can see that there's a difference between the original triangle in green and the image triangle in red, right? So this transformation, it looks like, is having the effect of kind of translating that triangle over to the right by a certain number of units. And if I pick different values for that constant a, I get different, what we would call translations. All we're doing is just rigidly moving the complex plane in some direction, and what direction we move it and by how far is just determined by the value of this constant a. Right? So we have a whole family of complex functions that all look like they're just translations of the complex plane. Multiplication is a little bit richer of a source of interesting ideas. If I'm multiplying my input value by the number 1, well, that's again the identity function, because multiplication by 1 doesn't do anything meaningful. But what if I multiply by, let's say, I? Right? So multiplying the complex plane by I looks like it has a different effect, right? It takes my green triangle here and it carries it onto the red image over here on the other side. This looks an awful lot like a rotation in some way. What about multiplying by 2i? Well, it still looks like a rotation, but also it looks like maybe my triangle's getting bigger, right? What about if I multiply by negative 2i? What if I multiply by negative 3, right? What if I multiply by something in between, like 1 plus I, right? So it's looking like multiplication has a different rich set of geometric effects that it can have, that maybe we're getting rotations, maybe we're getting reflections, maybe we're getting some other combination that aren't just translations as we did when we were adding. We already saw this example in a previous video, but as I start to mix more different kinds of arithmetic into my complex function, I can get more complex kind of behavior happening. This is the function 1 minus z over 1 plus z, where it's a little harder to say just with some certainty what exactly is happening here, but we can see some things happen, like, for example, if my input gets close to negative 1, my output tends to run off to the fringes, runs off to infinity. As my input gets closer to 1, my output gets closer to 0. So we can still learn a lot from this, even if it's not quite as simple as the previous two examples. I want to round this out by looking at two more families of transformations that have a very rich history in complex variables. The first is one that we're going to talk more about as we get into our fractals unit in a couple of weeks, which is called the Julia map. So this is just like the squaring function, except that in addition to squaring, we're also going to add a complex constant. In this tool, we're going to look not just at what happens to a single point, but also what happens to an entire kind of square drawn around that point. So if my constant is equal to 0, this is just the ordinary squaring map. And as I move this around, you can kind of see what the squaring map is doing, not just to a point, but to my square. And so you might ask a question like, well, what shapes are these that are delineating the boundary of the image, right? Once I take the horizontal and vertical line segments which make up my square in the domain, what are the curves that make up the image of that square in the codomain? So that would be something that if we understand the real and imaginary parts of this function, could help us to understand. And in this applet, I can also vary the value of my constant. So if I take c to be negative 1 plus I, for example, now we get, again, similar type of behavior happening, but maybe there's some more interesting behavior. So here's an example where my square looks like there's a piece that's almost getting twisted in on itself as we apply this transformation, right? So that the image is not even a convex shape anymore, but we're getting some weird self-intersection happening. And it might be worth thinking about what it would mean to have a self-intersection between this, like what's actually happening here from an algebraic perspective. That might mean that there's an example of a quadratic equation that has two different solutions, two different pre-images that have the same image. In other words, some point on this red side and some point on this purple side that are different points in the domain, but when I apply this function, they're going to the same point in the codomain. So these we're going to call the Julia maps, which is just like a squaring map, except that we're adding an additional constant onto it. And depending on what this constant is, we can get different types of behavior. And the second family of transformations I want to talk briefly about, but there is so much more to say about them, are called the Möbius transformations. Sometimes these are referred to as linear fractional transformations because they are nothing more algebraically than the ratio of one linear function of z to another linear function of z. And depending on what are the coefficients that we put in those linear functions, we can get a lot of different types of behavior in these transformations. So for example, here is another view of the same transformation that we already looked at before, which is 1 minus z over 1 plus z, except that now I have this square sort of sketched around it so we can see a little bit more about what's happening to horizontal and vertical line segments. One of the questions I'm going to have for you this week is, what are these curves? What do we think that these curves are that are the images of these horizontal and vertical segments under this Möbius transformation? And in our Desmos tool that we're going to use, you're going to have the ability to adjust the parameters of this Möbius transformation so that you can try and get a sense of what all this whole family of transformations has in common. So if I vary this a value, for example, maybe I'll take this b and make it negative. So I can just play around, and you'll notice that there's a lot in common between these different Möbius transformations. Ooh, this one looks a little bit different than that one in some ways. But there's some things that all of these transformations have in common, and this is a very well studied, there's a lot to say about Möbius transformations because they have a lot of really nice properties. So this is going to be, this sort of sets the table for the investigations that you're going to do this week. Let's take a quick run through the investigation problems just to kind of set up what they are and what I'm going to be asking you to do this week. So the main question is, in what ways can understanding the transformational properties of a complex function help us to illuminate its algebraic properties and vice versa? So in the first battery of questions, I'm going to ask you about this relationship between linear algebraic functions in the real xy plane and complex functions on the other side. So how do we achieve dilation, rotation, reflection in a couple of different ways? Or are there some things that linear algebra functions can do that maybe complex functions cannot do? So that's kind of the questions in 1 through 4. In 5 and 6, we're going to talk a little bit about this algebraic correspondence. So for example, question 5, how can we use a graphical transformation tool to argue for why multiplying by minus I is the same as dividing by I? So I want you to demonstrate that equivalence using algebra, but also use one of these tools to show graphically to a secondary student, for example, why those two things should be the same. Similarly, if we think about the reciprocal function, f of z equals 1 over z, one fun task is going to be to find out what are the real and imaginary parts of that reciprocal function, and then use your answer to see if you can explain to a student whether we should be rethinking the long-standing idea that our students have about whether we can divide by 0. Complex numbers, after all, give us this new opportunity to take the square roots of negatives that we didn't have before. And so a student might be inclined to think, well, what other rules that I take for granted might not hold anymore? And so this is a question about, well, how can we use a graphical tool to explore, as well as the algebraic tools here, to explore whether or not we can divide by 0, even now that we're in the complex plane. And then in 7 and 8, I want us to talk a little bit more about connections between the squaring map and the square root. Right? So we're going to bring the square root to the table a little bit in this pair of exercises. The first is going to be to leverage the rectangular and polar forms of complex numbers that we talked about last week to help us to determine the real and imaginary parts of a complex square root function. Because we can't just stuff x plus iy underneath this radical and then try and tease apart the real and imaginary parts using algebra, because we can't distribute that square root across the plus sign, right? And so using the polar form and some trigonometric identities is going to be a way to do this. As we'll recall, there's the same polar coordinate to rectangular coordinate transformations that we use in just studying the Cartesian plane are the same that we use to exchange the real and imaginary parts of a complex number for its modulus and its principal argument. And that translation is going to be the key to figuring out real and imaginary parts of a square root function for complex variables. Also, 8, this is probably my favorite exercise in this set of investigations. This is a great way to sort of take what our students in secondary school know about quadratics and how many zeros quadratic functions have, and try and import that understanding up to functions of a complex variables. How would we find zeros for a complex valued function? And how does the geometry and the algebra connect one to another? You can tell how much a math professor loves a question by how many subparts that they write. So I have parts A through F here. This is well worth devoting some time, because it's going to both help you to build your own understanding of what's happening here, and also this could be a really good activity you could take directly into your Algebra 2 class, for example, if you're talking about quadratics, right? So what I have you do is find an example of a quadratic that has a discriminant equal to negative 36. So the discriminant is the quantity underneath the radical in the quadratic formula, right? There's a Desmos tool for this as well. And then take that quadratic and run it through the ringer, right? If we interpret it as a complex function, how can we graphically, algebraically, using the quadratic formula and also using factoring, determine what are its zeros? And then our culminating set of exercises for this week are an investigation of the various power functions. So we've looked at the squaring function a couple of times. What happens if I vary the exponent? So look at z to the third power, z to the sixth power, z to the 1/2 power. What might that look like? What does that look like transformationally? And then in the culminating exercise, you look at Möbius transformations again, but then also Julia maps, and also another family of maps that includes a complex conjugate in it, and try and figure out what do these transformations kind of have in common. So coming back to the Möbius transformations one last time here, when I transform a square using a Möbius transformation, what I get doesn't look a whole lot like a square anymore. This image kind of looks like a chocolate chip cookie that's had several bites taken out of it, right? And yet there is still some stuff about this image that has in common to the original square. Is there some way we could argue that this image actually, despite having these weird sides, might still qualify as a square in some sense? And what is it, does that same kind of relationship hold for other kinds of complex functions? So that's the exploration that's going on this week. I look forward to working more with you over the course of the next week as you work through these ideas. Feel free to hit us up, chat with your team, chat with the rest of the class, chat with myself inside of the Discord channels for our course, and I look forward to seeing what you come up with.